Lesson 3, Accumulation Functions in Applied Contexts. The velocity of an object in motion is not only rate that we can integrate to get an amount. We have seen that accumulation or net change problems present us with a scenario where we are often asked to calculate the value of some quantity accumulated over time. We can solve the problems using definite integrals. Example 1, you received a 10-week-old Basset Hound puppy for your birthday and discovered that he is gaining weight at a rate of e to the 0.0125 t pounds per week, where t is the puppy's age in weeks. At 10 weeks, the puppy initially weighed 14 pounds. What is the expected weight of your new puppy at the end of week 15? So since they gave us that initial value, it was not at time 0, but it was considered an initial value. We can put that 14 first plus the integral from 10 to 15, because 14 was the weight up to 10 weeks. And now the integral is going to give us that additional weight from 10 to 15 weeks so that we can give an answer for the proposed weight or approximate weight based on this rate equation at week 15, at the end of week 15. So I went ahead and just put this one in my calculator. I know you could have done it, without a calculator by, taking the 0.0125 and dividing by that. So what I'm saying is that your integral would have been e to the 0.0125 t and then divided by that from 10 to 15. Okay, but I got 5.847 there. So the proposed weight at the end of week 15 is 19.847 pounds. Example number 2, an electric monorail transport is slowing down at a rate of 2t plus 25 feet per second, where t is the time in seconds. By how many feet per second does the monorail slow down between t equals 1 and t equals 5? So integral from 1 to 5 of 2t plus 25 dt, and this would be t squared plus 25t from 1 to 5. So 5 squared plus 25 times 5 minus 1 squared plus 25 times 1. So that gives you 124, and this would be feet per second. Example number 3, the number of liters of oil in a tank is changing at a rate R of t equals 0.26 t liters per minute, where t is the time in minutes. Initially, the tank covered 14 liters of oil. Write an expression that can be used to find the amount of oil in the tank after 10 minutes. So initially 14 liters of oil, and then if we integrate the rate for the next 10 minutes and add it to that 14, we should get the amount of oil that is in the tank. Okay, so initially 14 plus the integral from 0 to 10 v of t dt. So 14 plus the integral from 0 to 10, 0.26 t dt. 14 plus, I wrote it as 0.26 divided by 2 t squared from 0 to 10. So 14 plus, this would be 0.26 divided by 2, 10 squared, minus 0, so I'm not even going to write that. So I would get from this 27 liters. should be the amount of oil in the tank. Okay, example number 4. Describe the meaning of each expression in context to the given scenario. The function WT gives the number of water bottles produced by a manufacturer by time T in hours on any given day. Explain the meaning of the expression. So the integral from 4 to 8 of the derivative of W, I would explain as this equaling the number of water bottles produced during the 4th through 8th hours. Because this is going to be water bottles per hour. And so if I integrate, I'm going to get number of water bottles. Okay, so the amount of oil being drained from your pickup truck is decreasing at a rate of R of T quarts per minute, where T is the time in minutes. What does the expression below mean? So the integral from 3 to 4 of that rate is equal to negative 0.5. And if we're integrating a rate of quarts per minute, this is going to give us the number of quarts. Okay, so during the 4th minute, because remember, if it's 3 to 4, that's actually during the 4th minute. The amount of oil being drained from the truck decreased by a half quart. And if you started at 0, went from 1, and you integrated from 0 to 1, that would be during that first minute. 1 to 2, that's during the second minute. Because once you've hit 1, this minute's already gone. So this is during the second minute. And then, of course, and so on and so forth. All right. So Kevin got a gift of $500 from his grandparents for graduation. He deposited the gift into his college savings account. Kevin's savings grows each month at a rate of R of T, hundreds of dollars each month, where T is the month of the year. What does the expression below mean? So again, $500, he put it into his savings account, and it starts to grow. So he initially had $500, yet they're only showing 5 here. So this must be in hundreds, right? Like they said, R of T is hundreds of dollars. So if we put 500 here and this was in hundreds of dollars, that wouldn't have worked. We would have had too much money. So now they're saying that that initial investment plus the integral from 1 to 12 R of T dt is equal to 24. And so what this means, because he's depositing, it grows, however, we don't know how it's growing, but that is the rate at which it's growing. So by, by the end of the 12th month, Kevin's account had a total of $2,400 in it. And so kind of bugging me, sorry. I don't know why sometimes it writes like that. Okay, so example number 5. A city bus is accelerating from 0 to 18 seconds. The data for the acceleration a of t is recorded in the table below. If the velocity equals at t equals 0 is 6 feet per second, find the approximate velocity at t equals 18 using a trapezoidal sum. All right, so we know that our v of 0 is 6. And if I integrate acceleration, I'm going to get velocity. And they want us to give them an approximation for v of 18. And so we're going to say it's approximately equal to, and we're going to take our initial plus, and now we're going to use trapezoidal to do the rest of it. So we're going to focus on these first two, 1/2, and then this would be 3 minus 0, and then times my 1 plus 4, 1/2, this would be 6 minus 3, times my 4 plus 6, 1/2, this would be 9 minus 6, times my 8 plus 6, 1/2, this would be 12 minus 9, times my 7 plus 8, 1/2, this would be 15 minus 12, times my 7 plus 9, and then plus 1/2, this would be 18 minus 15, times my 9 plus 10. So, you know, you could keep, doing this the way you did, or you could notice that 3/2 can be taken out of everything, and that you have the first one once and the second one twice. The third one is twice. The fourth one is twice. The fifth one is twice. The sixth one is twice. And then the last one is once. Okay? And so this would be 6 plus 3/2 times 1 plus 8 plus 12 plus 16 plus 14 plus 18 plus 10. So I see 30, and I see another 30, that's 60, 79. So 6 plus 3/2 times 79 is going to give us 6 plus 118.5, which is going to be 124.5 feet per second. Example number 6. The graph at the right shows the rate in gallons per hour at which stormwater is being pumped from an overflowing canal. Find the approximate number of gallons pumped from the canal in the 24-hour period. And it says the approximate number. So we are looking to integrate from 0 to 24 this r of t dt, because that's going to give us our gallons of stormwater. Okay, because this is gallons per hour, and this is hours, so if we integrate that, we're going to get gallons. And so I'm going to use trapezoidal on this one, and so I'm going to say it's approximately equal to, I've got our 1/2. Each one of these intervals is a 4, so times 4, like, so 4 minus 0, 8 minus 4, 12 minus 8, 16 minus 12, 20 minus 16, 24 minus 20, and then times, and so you've got your first value at 0, which is 100, your y value is 100 here, and then you've got plus twice your second, so I said plus twice 125, plus twice your third, I said plus twice 137, So I said that that was about 137, plus twice. The next one, I said it was about 130. So about right there, I said, oops, this one was 137. This one was 130. Sorry about that. Plus twice 112. So this is the one that I said was about 112. Next one, plus twice, I said that one was about 85. And so you can see that your answer might have been different than mine if you chose different values for those. And if I was grading this on a test, I would have, taken that into account, that as long as you were close to 137, close to 130, close to 125, close to 112, I would have been fine with what your answers were, as long as it wasn't too far away. And so this gives me 2,696 gallons for an estimate. All right, example number 7, find the cost to produce 50 widgets if the initial cost is $1,800 and C prime of x is 155 minus 30x plus x squared. So we're going to let x be the number of items of a widget produced. Let C of x be the cost to produce x widgets. C prime of x is the marginal cost, the cost to produce one additional widget if currently x items are produced. That is, that C prime of x is approximately C of x plus 1 minus C of x, so that cost of producing one more. So they told us that C of 0 was 1,800. And we also know, since they're asking about 50 widgets, we know that C of 50 minus C of 0 is going to be the integral from 0 to 50 of C prime of x dx. So integral from 0 to 50, 155 minus 30x plus x squared dx. So 155x minus 15x squared plus 1/3 x cubed from 0 to 50. 155 times 50 minus 15 times 50 squared plus 1/3 times 50 cubed. And then minus, put 0 in for all those, you'll get 0. So this is going to be 35,750 over 3, which is approximately 11,916.667. So my cost of 50 should be 1,800 plus this. So $13,716.67. So the total cost of producing 50 widgets is $13,000.